I welcome you again for this NPTEL lecture on earthquake geotechnical engineering, and today we are at the lecture number 14, and this is related to dynamic soil properties. This is the fourth lecture on the dynamic soil properties, and it is on the field test, and third lecture on field test. So, today we will complete the field test, and in this lecture this is a part of the module 2 of dynamic soil properties, and we are under the chapter 2nd. There are 4 chapters in this module. So, chapter 2 on field test will be get completed today. As a part of the chapter 2, this is the lecture 14th here, and what we have covered in lecture 13, they are listed here. We talk about low strength test, which includes seismic refraction test, steady state vibration test, then we have SSW test, seismic cross hole test, seismic downhole and uphole test, and seismic cone test. What we are going to be covered in this lecture? Field test, that is high strength test, that is standard penetration test. Then we have cone penetration test, that is CPT, dilatometer test, that is DMT, and pressure meter test, that is PMT. And let me acknowledge that most of the information in this lecture is from the book by Kramer on geotechnical earthquake engineering. Coming to the high strength test, we already covered the low strength test using the field test using on high strength test. At the higher strength rate, behavior of soil is elastoplastic, and it produces what we call the irrecoverable permanent deformations. When you have the low strength, the deformations may be recovered, elastic deformations, but at a high strength the deformations may be irrecoverable and we have the permanent deformations. For geotechnical earthquake engineering problems, the following tests are of particular interest, which is one is SPT, standard penetration test. Then we have CPT, cone penetration test, dilatometer test, and pressure meter test. So, these 4 tests are there, which we are going to discuss one by one today, and all 4 are the field test, or 4 are finds in the category of high strength test, where you have permanent deformations. So, let us start with the first one, standard penetration test, SPT. SPT test is very widely used worldwide. So, this is the quite oldest test and most popular. So, you can categorize this is oldest in the field test and most popular. If we talk about soils, any test which is mostly the available data is available worldwide, not only in our country India, but even in US or Japan, that is SPT. And in the SPT, this is a standard penetration test and the oldest and most commonly. It is also commonly used in a number of geotechnical earthquake engineering applications. For example, liquefaction. When we will discuss the liquefaction, you can correlate the liquefaction resistance using the SPT data N values. And there is a code, IS code number 2131981, which is called method for standard penetration test for soil, which deals with procedure involved for SPT. So, what you have in this test is, in the SPT, a standard split barrel sampler is driven into the soil at the bottom of a borehole by repeated blows, and these blows are 30 to 40 blows per minute of a hammer. The weight of the hammer is 63.6 kg and it is released from a height of 76 centimeter. So, what you have? You have a hammer. Why it is called standard? Because many things are standardized. The weight of the hammer is standard 63.6 kg, it is fall from a height of 76 centimeter, and number of blows, rate of the number of blows is about 30 to 40 blows per minute. The standard SPT sampler should have a constant inside diameter. The use of sampler designed to accommodate internal sample liners can underestimate penetration resistance by 10 to 20% when the liners are not in place. The sampler is usually driven 450 mm. The number of blows required to achieve the last 300 mm of penetration is taken as the standard penetration resistance N. So, when we penetrate, actually what is done in this SPT, you drive your sampler total depth 450 mm, and this depth 450 mm is divided into 3 layers, each layer is of 150 mm. So, this is 3 layers. So, I start from top and this is 150 mm, then another 150, that is 15 centimeter, and the last one is 150, another 150 mm. So, the first layer 150 mm, this is called what we call the sitting drive, and last two layers, this is 150 and 150 mm. The number of blows required, for example, in the first layer number of blows required is N1, in the second layer N2 and then N3. So, N will be simply N2 plus N3. We do not count the number of blows required to penetrate the first layer, which will come under the sitting drive. The N value is a function of the soil type, confining pressure and soil density, but is also in by the testing equipment. So, here basically N will represent, this N value will represent your strength. So, here strength will be represented, and this is basically strength which is shear strength. And this will be influenced, that means if you have N better N, in that case your shear strength will be high. In standard penetration test, you have here a sampler, you could see the setup of SPT here given. So, you have like this is donut hammer and the slip or guide. So, what you do, and you have the rotating like what you have this rope, in fact this is chain, this is, and this is goes from the pulley, and when you do it like that when you move it, it go up and down, when you release it here it will come down, when you stretch it then it will come up. So, what is done here, you lift the SPT hammer up to certain height and you drop it and again drop it, one blows, second blows, third blows like this, and then you count the number of blows to go that this part at certain depth. So, you have the borehole inside this one, and this is anvil where a strike is done, and then you have drill road. So, this way the SPT, this is the schematic of the SPT. Now, continue with this, the data which you get from SPT requires some corrections for different purposes, and it is very common to normalize the N values to an overburden pressure of 100 kilopascal, because the overburden pressure in the field will be different, particularly at different depths. So, what we do, we normalize this overburden pressure to what 100 kPa, that which is roughly 1 bar, and to correct to, and what we call the, and then we apply correction and energy ratio of 60%, and this 60% ratio is, what is this ratio? The average ratio of the actual energy delivered by safety hammers to the theoretical free fall energy. So, you have actual energy and the free fall energy. So, you have N160 Nm Cn, and so this is the way here this equation is. So, in this case you have this number of measured penetration resistance, and Cn is overburden correction factor, and what is you have in this case penetration resistance and over. So, one, this is the measured value Nm, Nm is the measured value from the field, Cn is the correction factor, and then this correction is for overburden, this correction Cn is applied for overburden, the last correction this is due to the energy. In this case Em is the actual hammer energy and EFF is free fall. So, suppose normally if suppose you have Em equal to 0.72 EFF, if I have this case, so this factor will becomes 1.2, and for the conservative side minimum will be 1. So, normally this energy correction will not be less than 1, then overburden correction will give you the values of how Cn varies with the depth, and Cn will be different at different depths. So, the values of Cn, and this is also like in the this code also there is a code for that, and that also says about these corrections. This N160 values which is recorded from this SPT, they are after correction they are used for the liquefaction analysis. For gravelly soils, the another test what is called Becker hammer penetration test can be used, and it is used in the same way as the SPT force sense. The BPT resistance is taken as the number of blows per foot of penetration corrected for diesel hammer or in the bounce hammer, which reflects the effect of soil and the combustion. So, this is about a Becker hammer. So, with this complete SPT. Now, the second test, which is called cone penetration test. One thing I will like to point out here about the CN, which is I think somehow it is missed here in the slide. So, how the CN, I can use this space. When you have with the depth, what will happen, your CN values are like if I have here, when I increase the overburden pressure, if my overburden is about 100 kPa, then the CN should be 1. So, this is one value and this is the lowest value. So, this like you have, it varies like it will go 1 and then it may be more than 1. So, it may be 2 here. So, this curve goes like this one with the So, this value is roughly this is CN on x axis. So, this is 0.4 and this value is about 1, which is at 100 bar 100 kPa depth, and if you go at the most it can go up to 2. So, CN typically like taken, the value of CN correction should be between 0.4 to 2. It should not be less than after applying the corrections, and there is equation for the CN which is for calculation of the CN equation. .77 log 10, then you have 2000 sigma V0. This is the equation. So, you use this equation. What is in this equation? Sigma V0 is like I can write it here only, is effective overburden pressure. And this effective overburden pressure should be in kilopascal. What you have in the second test after once we done with this, so you use CN and then these corrections and then you find N160 value. Now coming to the CPT, which is called cone penetration test. The CPT involves the steady penetration of a standard cone penetrometer into the ground, and this standard cone penetrometer has a conical tip of 10 centimeter square area and 60-degree apex angle immediately below a cylindrical friction sleeve of 150 centimeter square surface area. So, like SPT, in the CPT also many things are standardized, and what are the, you have the cone which have a tip and the area of the tip is 10 centimeter square, and that is an apex angle of 60 degree, and this area and apex angle, they are immediately below a cylindrical friction sleeve, and the area of the friction sleeve is 150 centimeter square. The penetrometer is pushed into the ground at a constant rate of 2 centimeter per second. So, we push like penetrometer in the ground, and this will be pushed at a like that at a, like in the SPT also number of blows, rate of the number of blows was constant. Similarly, in the CPT you have number of rate of this penetrometer is 2 centimeter per second. The typical example of CPT is given here. So, in the CPT you use some mechanism like a truck or like on the top, which is used for rig with hydraulic pushing system, but even it is can be done without the truck also, but then machine will be like loading, a penetrometer goes inside this inside the ground. So, what you have here in this case, this in this figure which is enlarged, and this enlargement has been done for a cone, showing the detail for the cone. You have the cone, and in this case cone you have sleeve friction resistance which is Fs, you have cone measured tip resistance which is denoted as QC. So, you have QC, what are the parameters which is measured, then you have Fs sleeve friction, and you get the total cone tip resistance where, and then another item which is pore water pressure. pore water pressure, to measurement for the pore water pressure, you require what is called piezo cones. Piezo cones are used for the seismic piezo cones, which are used for measurement of pore water pressure. So, to measure U in the field at different depths. So, that is also possible using CPT. In the CPT, the tip and friction sleeve are each connected to load cells that measure the tip resistance QC and sleeve friction resistance Fs during penetration. The friction ratio, which is denoted by this ratio Fr, which is Fs divided by QC. Friction ratio will be this ratio, and this is also a useful parameter, and it is this ratio is high for cohesive soils and it is low for cohesionless soils. The absolute and relative magnitudes of the penetration resistance can be correlated to the many of the same properties of the SPT and also to soil type. So, many data like which is like you have the correlations with the data with the SPT and CPT data, which is like some correlations are available in the literature. How the typical results for CPT looks, which is given here. In case of CPT, cone penetration test, you have different results of the friction resistance, how the friction resistance is varying with the depth, which is shown in this figure, and then you have which is tons per feet, while bearing resistance is also given in this figure, which is tons per feet square. Friction ratio will depends on your, as we discussed, is this is sleeve friction and cone penetration. So, Fs is sleeve friction and while QC is tip resistance. So, if you divide sleeve friction by tip resistance, then you get the friction ratio, and you see the friction ratio also varying. In this case it is varying from 0 to 6, and with the depth variation is quite large. The CPT can be performed rapidly and relatively inexpensively, because in CPT you are that you are just continuously pushing inside, you are not taking it out like because no sample is collected in this case. So, you are just pushing your penetrometer with certain rate inside the ground. It provides a continuous profile of penetration resistance that can detect the presence of thin layers or sand that are easily missed in the SPT testing. The capabilities of cone penetrometers can be enhanced by adding additional transducers to measure additional variables such as pore water pressure, piezo cone or wave propagation velocity. So, this can be done. Now, continue with cone penetration test. How the CPT cannot be used at sites with very steep or very dense soils without damaging the probe or roads. So, if you have very steep site, what will happen? The cone will get damaged when you push it inside, for example in the rock, then it will damage its cone and it is difficult to conduct this test. The presence of gravel size particles can also limit the use of the CPT. If you have the large gravels in the, then it is no sample is collected like what is done in SPT, and there is a code like SPT have also IS code for the CPT also 4968 part 3rd of 90, which is method for subsurface sounding for soils, that is involved for CPT. So, this was about CPT. Then the third test for the high strength testing in the field is called dilatometer test, that is in the short called DMT. The dilatometer test or DMT use a flat dilatometer, and dilatometer is nothing but a stainless steel blade with a thin flat circular expandable steel membrane on one side. The dilatometer is jacked into the ground with the membrane surface with the surrounding blade surface. At intervals of 10 to 20 centimeter, penetration is stopped and the membrane inflated by pressurized gas. So, in this case pressurized gas is used, and this pressurized gas is used after once penetration is stopped, and the membrane which is there, that will be inflated by this using the. Continue with the dilatometer. The pressure at which the membrane moves by 0.05 mm, that is the what is called the lift of pressure, denoted as P naught. So, one is the lift off pressure P naught, and the pressure at which its center moves, that is 1.1 mm about, that is P1, they both are recorded. So, you are recording two things, the lift off pressure and another pressure which its center moves by the certain distance. So, one pressure is P naught, another pressure is P1, and these are used with the what is called hydrostatic pressure U naught and the effective overburden pressure sigma V naught to compute various indices to which soil properties can be correlated. So, you have lift off pressure P naught, you have the pressure P1 by which the center moves an amount of 1.1 mm, hydrostatic pressure and effective overburden pressure. So, these four will be used to calculate the indices in the dilatometer test. These indices are given here. So, in these indices you see the most commonly used indices are the material index, which is called ID, the horizontal stress index, which is called KD, and the dilatometer modulus ED. And in the first case you have P1, P naught and U naught, 3 are involved. In KD effective overburden pressure is also involved, and in ED this is alpha multiplied P1 minus P naught. So, you see the ID dimensionless, no, it is ratio. Same thing is KD is dimensionless, but ED, which is dilatometer modulus, it will have the same unit as P1 or P naught, alpha is dimensionless. So, dilatometer test, how it looks, this is given in the figure. So, you have flexible membrane which is about 60 mm in diameter. So, diameter of this is like 60 mm, and then you have 90 mm is the outer shaft. So, this is the elevation, first part is the elevation and the second side views are there. So, two side views are there. So, in this case you have a wire and you have a pneumatic tubing which goes inside this, and like thickness which is basically diameter of this your cone which is here about 14 mm is there, and then you are applying the pressure from the side, and similarly. So, this is what we call the flexible membrane is there, and these are the pressure measurement. So, this is side views of the fluid dilatometer. So, this was, and then in this equation ED, which is for dilatometer modulus, alpha is equal to 34.7 for a 60 mm membrane dilatometer and a membrane deflection of 1.1 mm. So, if dilatometer is 60 mm and 1.1 mm deflection, then you get the alpha value 34.7. Dilatometer parameters have been correlated to low strain soil stiffness and liquefaction resistance. So, they have been used for that. The last part for high strain testing is what we call the pressure meter test. In the pressure meter test, PMT is the only in-situ test capable of measuring strain, stress strain as well as strength behavior. The pressure meter is a cylindrical device that uses a flexible membrane to apply a uniform pressure to the walls of a borehole. So, you have this in the pressure meter test, a cylindrical device is used, and the cylindrical device was used in there also in the dilatometer, and it uses a flexible membrane which is to apply a uniform pressure. So, let us see how it like this looks, pressure meter test. Deformation of the soil can be measured by the volume of fluid which is injected into the flexible membrane or by feeler arms for pressure meter that use compressed gas. After correcting the measured pressures and volume changes for system compliance, elevation difference and membrane effects, a pressure volume curve can be developed. So, when you want to develop the from the output of the pressure meter will be pressure volume curve, that is how much, because there is a fluid is used, and that that fluid volume of that fluid is used for the measurement of the like the pressure to measure. So, but to generate pressure volume curve you need to apply corrections, and that corrections are related to changes for system compliance, elevation differences and the membrane effects. So, these are done, and this pressure meter test setup is given here. You have a control unit on the top, you have a borehole and cylindrical flexible membrane which pressurized by the fluid, and so it goes. So, volume is known and the pressure which goes inside this borehole, that is also measured, and by these calculations we calculate the the level of because at this high strength and it is happening at the high strength. So, we can calculate the properties of the material. Using cavity expansion theory, the pressure volume curve can be used to compute the stress sustain behavior. So, this will be used for the stress sustain behavior characteristics. Self boring pressure meters which minimize soil disturbance and push in pressure meters which can penetrate soft soils very quickly have also been developed. So, with this we complete the field test using high strength test. So, in fact, with this we complete chapter 14 and we completed 2 chapters of the module 2. One is was stress condition, another is on the field test. So, now we will in the next lecture we will discuss chapter 3rd, which chapter 3rd on this, and chapter 3rd is on the laboratory test, and we will in the chapter 3rd we have again 3 lectures including in the laboratory test both low strength as well as high strength test. So, thank you very much for your kind attention.